the agenda today is actually based on or using some exercises from a class that we have taught traditionally, although not recently, called interpretive mapping. There's some excellent exercises in there that have to deal with some of these advanced features in IsoMap, including grid operations. And the example I'm going to use has to do with trend surface and residuals on what is interpreted as a meteorite impact structure in northwestern Oklahoma. Then going to look at surface substitution, a little bit about how radius of influence can affect your results with gridding and contouring. And then also using the Geologic Bias Option. It's one of my favorite exercises actually in that class, and coupling that with surface substitution. And then if there's time, I'd like to talk a little bit about using the Composite Formation Top tool in WellBase to, first of all, to map an unconformity, and then also to talk about how it can be used for renaming tops. And if we don't get to the Composite Formation Tops, please feel free to email any questions or comments you might have, and can answer those one-on-one or whatever. Okay, so without further ado, I'll go ahead and start the demonstration. I'm going to start with a project called Astrobleem, that meteorite impact structure. And what I'm going to do is go ahead and open GeoAtlas and open a map called Start, which has the key layer called the Sylvan Wells layer. The Sylvan is an Upper Ordovician shale succession, I believe, in Oklahoma. What we're going to do is do a structure map on the Sylvan shale, and then a first order polynomial trend surface on the Sylvan shale. Of course, first order trend surface is a simple plane cutting through the data, and then we will subtract the structure map from the regional structure based on that first order trend surface map and see what's left over, and hopefully the Astrobleem or meteorite impact structure will still show up. So let me go ahead and make a quick structure map. So contour, build surface, and let me go get my little cheat sheet here of layer names so I don't have to type them in. This is going to be the top subsea Sylvan. I'll add a data source from WellBase, of course. Top subsea here, Sylvan. Somewhere, where are you? There you are. Default source is our only source, okay. And I'll go ahead and finish that guy without changing too many of the parameters at this point. And so there is our Sylvan structure map. Okay. All right. Now I'm going to go ahead and build the trend surface layer. So go ahead and go contour, build surface. Give me a similar workflow, and this is going to be called the Sylvan first order trend surface. There we go. Piece of cake. Add the WellBase data source. It's also going to be the Sylvan top subsea. There it is. Default source. And in this case, I'll go next. In this case, in the build parameters gridding algorithm, I'm going to choose trend. And down here under other, we're going to have our various orders of polynomial trend surfaces. Okay, we're just going to do that simple first order trend surface, and just to make it stand out from the original structure map, I'll go ahead and click on the options next to contours and color these contours red, both bold and regular here. There we go. Okay. Finish. And so there you can see our simple first order polynomial trend surface dipping. There's negative 6400 and there's negative 7,400. So it's dipping down from northeast to southwest. Okay, all right. Now I'm going to go to Contour, IsoMap, Grid Operations. This is where we're going to do our grid subtraction operation. And this is going to be called our Sylvan Residual. Okay. And I could do a simple A minus B and assign my grids, but we do have some equations in our equation editor, or some standard equations you can use to cheat with. There's the residual equation, structure minus trend. Those are our variables. I'll select that and say OK. And it parses our two variables. So your output grid is going to be your result, the Sylvan Residual. And it's going to be the structure map minus the trend surface map. So we need to assign our grid variables, if you will. We need to assign our layers. So the structure layer is, and I'll hit select, the top subsea Sylvan, and the trend surface is, of course, the first order trend surface. And one of these needs to be set as the key grid, grid spacing, etc. Those kinds of parameters need to be assigned to the resultant grid from one of the two grids here, and I'll go ahead and set the key grid as the trend surface grid. Okay, and also I want to go ahead and interpolate the new values that are going to come out on that layer to the data points. So that's what that interpolate data points is all about. Next. Okay, and go ahead and perform the grid operation. And again, I will go ahead and leave my defaults. And now what I'll do is I'll turn off the eyeballs on the top subsea and the first order trend, and I'm left with the anomalies, if you will, in that Sylvan structure map, where I've taken the regional trend out, and I'm left with this strange circular structure that's been interpreted as the Ames impact structure in the late Ordovician. Okay, so that's a simple example of grid operations, subtracting grid A from grid B. Another place where that could really come in handy is if you happen to do a lot of either hand contouring or hand editing of machine generated contours to generate your geologic concepts, your geologic maps. If you do that with a couple of surfaces and you want to get an isochore, you want to get a thickness map as a result from your interpretation, you would take your edited maps or your created maps, as it were, hand created maps, do a contour to grid operation. So you end up with two grids based on your interpretation of the data, and then subtract one from the other to get a resultant grid, a grid operations layer, as it were, that reflects the thickness based on your interpretation. That would be another common use of grid operations. Okay. All right. So let me go ahead and close that map, and I'll move on to a surface substitution example. So I need to change projects here. I'm going to go to what's called the structural surface substitution project. Activate that. Okay, I'll go back to GeoAtlas, and I'll create a new map, and I will grab this top subsea GGLM layer. I'm not sure what the GGLM is, but bear with me. Here it is. This is a structure map, and you'll notice that there's some rather crazy edge effects here. In fact, if I go to the entity filter and I make sure that data point is the only entity that I can actually select by unchecking everything else, I can use my selection arrow, draw a box, and I guess you can make out those blue highlighted data points. So you can see they're clustered in the central 50% or so of the map, so that's why we're getting these crazy edge effects. Now, a lot of times people will mitigate the problems associated with those edge effects by using a boundary polygon, right, that will null out all the grid nodes in the AOI or the project outside of that boundary polygon. But there's another option that you have, which is actually a surface substitution option. So in this case, we actually have a quote-unquote regional structural model that can be substituted in areas where we don't have actual structural control. So what I'm going to do is create another map so we can look at the two side by side using this GGLM regional model. There we go. And then I'll tile the two maps vertically. As soon as this other guy gets created, there he is, and I'll go Window, Tile vertically. So there's our structure map with its attendant edge effects, and there's the regional model. Now, one thing I want to show you kind of in anticipation of what we're going to see at the end here, I'm going to go over to this map of the structure, and let me go back to Entity Filter Contour so I can actually hover over a contour and get a value. And so you notice we have here, let's see, negative 775, and as we go to the northeast, negative 765. So we're getting structurally shallower to the northeast based on the edge effects. Okay, and that's because it's substituting an average value of the structure values, an average value in the areas away from the data. Whereas here in this map, let me make sure my entity filter is allowing me to, yep, contour is selected. Here we're going from negative 840, let's see what this guy is, negative 900. So in the regional structural model, we're getting deeper structurally to the northeast as opposed to shallower based on the substitution of the average value. So keep that in mind, right? Okay, all right. So now I'm going to activate the map with the regional model. All right, and I'm going to create a new surface, Contour IsoMap Build Surface. All right, and this guy is going to be called, let me copy my map name here, there we go, GGLM sub C with surface substitution, radius of influence 1000, so you know where I'm going with that. Okay, now I'm going to add a data source, which is going to be an existing layer. It's going to be my, we're actually going to add the data points from that structural layer. So existing layer, okay, and then the GGLM top sub C, there we go. All right, let me just double check here. Yep, we want to make sure that we don't do the contours. We actually want to use the data points. Okay, so we're actually, again, when you use an existing layer and you have multiple entities on it, you have to be real careful which of the entities you actually use. So we're going to use the data points off of this layer over here. Okay, so add that. All right, okay, next, now we're going to go to the grid spacing tab, and we're going to change that radius of influence to 1000. So what that's going to do is that's going to say, okay, my final layer here that I'm creating is going to essentially, once you get 1,000 feet away from a given data point on that original structure layer on the right there, we're going to look to the substituted surface to control our contours. Okay, so that's the important thing. So the smaller the radius of influence, right, the less the distance it looks away from a given data point for control. So that's the idea there. All right. Now we're going to go to the Geologic tab, and we're going to do a surface substitution. Notice that the default is to use a z-value, which turns out to be about the average z-value for the data. And again, that's why we were apparently shallowing to the northeast structurally. However, when we put our surface in there, our regional model, there we go, it's going to use that rather than that average value. Okay, all right, next. Play with the contours a little bit right here. We're going to go negative 1,000. Override defaults, right? Negative 1,000, negative 500. There's our contour range. All right. Finish. Create our new guy. And I'll get the regional off of there. I'll close the eyeball on the regional model. All right. So there is our new layer with the data points controlling the structure, if you will, in this central area, and then the surface that we used controlling the configuration for the most part of these contours out here. And again, -850, -875, -900. So we are getting structurally deeper, and that's purely based on that regional model that we used. Okay, hope that makes sense. So that's a little bit of surface substitution. Okay, I am going to switch gears a little bit and go to an exercise that I've always found to be one of my favorites, involving using bias direction and also surface substitution in a rather interesting geologic scenario. So let me go ahead and close these two maps. I'll minimize GeoAtlas, and I will change my project to the Powder River project. There we go, and I'll activate that. Okay. Now this is a rather involved exercise, and I've sort of paraphrased it, so it's not going to be as involved as it would be if you were taking this 2-day interpretive mapping class, but I'll try to give you the gist of it here. Okay. So first thing I'm going to do is I'm going to open a map called Lab 1 showing you the well control in the area. And it's kind of an interesting, let me maximize this guy, it's kind of an interesting scenario. So these are muddy formation channels, these orange well spots, okay? And it turns out that the brilliant geologist who put this together created filters for the channel wells, you know, essentially isolating the channel wells in a filter, and the what I call the background marine wells, these yellow guys, in a filter as well. Okay. Now, I notice I have some layers over here. I've already created these layers, and so these three layers are actually muddy to Skull Creek Formation isocores, and I'm going to go ahead and turn the eyeball on the all wells muddy to Skull Creek isocore. So you can see that there's some influence certainly with these channel wells, but rather smeared out, and the channel orientations don't necessarily track very well in some places with the channel wells themselves, because you've got a lot of influence coming in from these marine wells, okay, that don't have any channels in them. So it's a little bit smeared out. Okay. Now, so that's the all wells. Now it turns out you can, because we have these filters, we can make layers that consist of the channel wells only and the marine background units, if you will. So I'm going to turn off the all wells isocore and turn on the channel isocore. Okay, so this particular isocore map consists of data from the channels only. Okay. And again, you can see that there's humongous edge effects, if you will, similar to what we saw in the last exercise, because we don't have any data away from those orange channel wells. Okay, so that's what that guy looks like. And then if you want to, let me make sure I don't have to do anything before I move on here. Not at the moment. So I'm going to go ahead and close that eyeball, and I'm going to go to this muddy Skull Creek background marine isocore, which is essentially all the non-channel wells, and you'll notice there's a completely different orientation. So shoreline trend is clearly northwest southeast in this area, and then during relative sea level fall and channel incision, these channels were cruising across from the northeast to the southwest. Completely different orientation. So we really do need to have two bias directions. In fact, I'm going to go back, before I show you the bias direction in the marine, I'm going to go back to the muddy Skull Creek channel isocore, and I'm going to update the layer and double check and see if we actually have a bias direction built in here. So I'm going to go to Build Parameters, Geologic, and it turns out we don't have a bias trend. So I'm going to go ahead and put a magnitude 3, and this would be something you could play with empirically, the different magnitudes, how it affects the appearance of your map, etc. So I'm going to go ahead and put a magnitude 3 in here, and I want to make sure I get this guy right. It should be a 10 degree, or nope, this one's going to be a 45 degree bias. So it's kind of a compromise bias, because it turns out there's 3 different biases, 3 different channels, 3 different orientations, I should say. But in any event, we'll go ahead and do the 45 on here, and notice it automatically says, hey, we're going to regrid because we need to create a new grid based on that bias. I'll go ahead and finish that. So this is what the channel map looks like with that 45 degree bias, and you'll notice that southerly channel does appear to have about a 45 degree bias, and you see a lot more elongation and alignment of the contours along the 45 degree axis, if you will. And then let me go ahead and close that eyeball and go back to my background marine and update that layer, and I'll show you how that guy was created real quick bias wise. So under Build Parameters, Geologic, notice that we've got again a magnitude 3 bias at 135 degrees, which is that it's injecting that northwest southeast bias. So I can go ahead and cancel that. So that's what we're seeing here. Okay, so what I'm going to do next is create a layer that involves both of these bias directions. Okay, so I'm going to go ahead and minimize this map. I'm going to open my what's called Start map. Where is it? There it is, the start.gmp. Okay, there we go. All right, so here is one of the Muddy to Skull Creek isocores. This one happens to have a 10 degree bias. I'll turn the eyeball on and set this guy active over here in my layer display toolbar on the left here. Okay, and I need to double check and see if I've actually set this to 10 degrees. So I'm gonna, I'm gonna update active layer, go to my build parameters, geologic, and nope, no bias trend here. So what I need to do is set this guy to magnitude 3, 10 degrees. Okay, so it's almost north-south. There we go. Okay, and I will, again, it's going to regrid, so I'll hit finish. All right. Whoops, I forgot one thing. Only the most important thing. Let me go back to update active layer. All right. In addition to the bias, I'm going to substitute the marine background layer, if you will. I've actually made a copy of it, and I called it Marine Background, or Muddy Skull Creek Background Marine Isocore Source. Okay, and we're going to add that, and that is going to be our Surface Substitution layer. Okay, and what we're going to do is we're going to drop our radius of influence like we did in the last example to only 1,000 feet. So again, once you get 1,000 feet or so away from one of these channel wells, it's going to look to the marine background isocore for guidance on how to contour these Muddy to Skull Creek values. Okay, hope that makes sense. All right, and again, it's going to regrid, and let's see what we get now. All right, so now we have, as a result, a layer that incorporates both bias directions. Okay, the channel wells are the main source of data, and they're biased north 10 east roughly, and then away from the data, again 1,000 feet or more away from the data, this grid is utilizing that marine background source layer to create the isocores away from the channels. Now the exercise is actually a little more involved in this. It actually at the end of the exercise, you have 3 channel bias directions incorporated into a single layer. It's actually a pretty neat exercise. Okay, and by the way, if you wanted to play with the radius of influence, as I mentioned, you can go back in here, update active layer, and let's see what happens. I haven't actually played with radius of influence too much in here, but let's actually do it here while we're doing the webinar. Whoops, grid spacing, and I'll change the radius of influence to 5,000 feet, which should essentially this essentially means that channel wells are having more influence on the map, certainly proximal to the channel. So I'll OK that. And let's take a quick look at this. In fact, whoops, it's gone. I should have taken a screenshot, but that's all right. I'll go ahead and regrid, finish. Okay, and again, I'd have to have a screenshot to tell, but in theory, right, these channel wells are having a lot more influence, or at least having influence farther away, and these should be sections, so 5,000 is about the width of a section. And I think you're going to see some more bending of the marine toward that channel orientation is what we're probably seeing. A smaller radius of influence would have a different effect. Let me go ahead and take a screenshot here since I want to kind of curious myself. I'll grab that area right there. I'll put it over on my other monitor. I'll update the layer. And I will go to build parameters, grid spacing, and let's make the radius of influence 250. So we aren't getting very far away from the channels at all. Doesn't like that. It's got to be, that's right, it's got to be more than the smallest feature radius. So I'll go back to 400. Haven't got caught by that very often. There we go. And regrid, finish. Okay. And now maybe there's a little difference. Probably need a bigger radius of influence. There's not a lot of difference there, to be honest with you. One thing that a smaller radius of influence will do, however, is it will create a lot more localized closures. So as I glance at the 2 maps, and you can't see the other one, I'm going to keep that away from you. You do have a lot more isolated closures because of that smaller radius of influence. So again, if you have a geologic play where you do have porosity pods or pinnacle reefs or whatnot, a smaller radius of influence will guarantee you that those areas actually are represented by closed contour is probably what you want. Okay, all right, now I'll go ahead and close this guy. And I do have a few minutes here, so I do want to show you that example where we use the Composite Formation Top tool. So I'm going to go to one more project. Almost done. So I'm going to go to the Alberta Basin Unconformity project here. I actually have an interesting map. Hopefully I saved it. Let's see. Of course not. Let me double check and see if there's an AOI. No, there's no AOI. So I'm going to make a new map real quick. Try not to take too much time here. I'll use this layer called Wells with Tops. Notice it's got conditional pies associated with it. And I'll put land grid and prospect wells in here too. Okay. There we go. And this map was actually made with our virtual conditional pie tool, right? Where we actually took and looked at formation tops, all right? And so we used wells with tops 3 different times. Again, I don't want to spend too much time on this, but I don't want this layer to be a mystery either. And then the 3 tops were, hopefully I'll get this in the right order, Nisku, Upper Ireton, where are you? There you are. And then the Grossmont. There we go. That's how it was created, okay? And the colors are Nisku red, Ireton, Upper Ireton green, Grossmont blue. So essentially what this is pointing out is the fact that you have regional truncation across this area. And just to show you this geologically, I created a little model in geomodeling, right? You're not going to get a webinar from me too often where I don't grab geomodeling and pull it up for some reason or another. It'll come up pretty quickly. It's called regional unconformity, and this will give you a pretty good visual on what we're looking at here. And then I'll go ahead and use that Composite Formation Top tool to create an unconformity. I'll probably drag you guys into a webinar at some point in the near future where I go into some of the tricks you can do with geomodeling related to regional unconformities, subcrop plays, fault polygons, transferred to isomaps, you know, all my favorite things therein. Okay, so here we have a cross section through here, and I'll go ahead and open it. It's just a essentially a well-to-well cross section with no wells. There it is. Go ahead and zoom in on the darn thing. And so what we're looking at here are these three units being truncated across an unconformity. Okay, and let's see, turn some of these guys off, and you can see that the units, it's not a completely finished model, obviously, but the bottom line is you're getting the younger units truncated to the west. Now, the way this works geologically is that you can see that the younger units are picked to the west, and the upper Ireton here in the central part of the area, and the Grossmont to the east, and those units are sitting under the unconformity. So in order to map the unconformity, we actually have to create a new surface that uses either the Grossmont, upper Ireton, or Nisku as the indication of the unconformity, right? It depends on which ones are picked. So what I'm going to do is go to WellBase, show you how this works. There's this tool called the Composite Formation Top tool, and again, it has multiple uses, including renaming tops. And what I'm going to do here is I'm going to create a new formation. This doesn't delete anything from the database. This simply adds data to the database. I'm going to call this thing Unconformity. This is my new top with the same source default, and well, lo and behold, the grid actually populated itself because that's how I had left it. So what I did was I added three formations, the Nisku, the upper Ireton, or the Grossmont, and essentially what this does is it looks at each well and it says in hierarchical order, hey, have you got the Nisku in that well? Oh, you do. Okay, we're going to assign that that measured depth value to the new top unconformity. No Nisku, let's look for the upper Ireton. No upper Ireton, we'll look for the Grossmont. If it doesn't find any, it doesn't create the unconformity. But essentially it's creating the unconformity based on this hierarchy of these three formations. Now I can hit create update. You'll go ahead and calculate. Should be done. Go to formations, and notice in this particular well we have Nisku and we have unconformity. This was just created, and you'll notice they have the same MD. Okay, and I can cruise through these wells here, and if you find one, let's see, in fact let me go back to the map. Let me grab some wells where we have upper Ireton only. There we go. View the wells in WellBase. And now the unconformity should be assigned to the upper Ireton, and it is. Okay, so now I can go back to our friend GeoAtlas, and I'll go ahead and hide the wells. Well, I'll leave the wells with tops on for now, and I'll simply do a contour build surface on that unconformity. Okay, and I'll just call this unconformity sub C. So this will be a structure map of the actual unconformity. Add my WellBase data source, you know the drill. Top sub C, unconformity, where are you? There you are. Default source, life is easy, there we go. let me tweak the grid spacing a little bit to get a little better fidelity on this guy. And just for grins, I'll do a color density fill. See what we end up with here. All right, so there's the subsurface expression of that unconformity based on using the Composite Formation Top tool in WellBase. And just one more word about this. So again, it's not the easiest thing in the world to do, right? To change a top name in WellBase. But the Composite Formation Top tool can be used to do that. So if, for example, I wanted to change the name of one of these guys, let's say I wanted to change the Ireton to the Ireton Formation for some reason. Okay, that's going to be the corporate name from now on, the Ireton Formation. I could go ahead and then add my source formations. Ireton, you're around here somewhere. And you could actually do this in a hierarchical manner based on the sources that you trust the most, right? With yourself at the top, of course, and then some of your fellow geologists cascading down all the way down to the intern from last summer who you put at the bottom, or maybe you put IHS at the bottom, I don't know, up to you. In any event, that way you can change the Ireton to the Ireton Formation, create update, and now we're going to have in wells where we have the Ireton, and of course one of my problems here might be it's not in my, yes it is in my strat column. Hopefully it was picked, but the bottom line is you'll get an Ireton Formation in here. Yes, I'm doing this ad hoc, so apparently I haven't gotten any wells that have it. And then you can actually go into Strat Column Manager, put the Ireton Formation in the right place, right? Up here next to Ireton. And then if you needed to, you could, from public, you could actually delete the Ireton so it's gone and you only have the Ireton Formation. You haven't lost anything. Okay, just wanted to show you guys that. Okay, so appreciate it, appreciate your attention. I guess I did run a little long, but in any event, as usual, please let us know what questions you might have. In addition, since everybody's hunkering down these days, I've been doing a fair number of kind of one-on-one or one-on-two go-to-meeting sessions, little mini training sessions, or looking at individuals' projects, etc. So if you're interested in any of that, please contact your sales rep, who will contact me, and we can get together and maybe play around with some of these options that you have in IsoMap, or look at any of the other problems or issues you might have.